Next, we're going to talk about angles drawn in standard position. So to study circular functions, and that's sort of what we're moving into, we talk about these advanced functions. There's a certain collection of advanced functions that have to do with circles. So we call them circular functions. So we're a long ways, we're not there yet. We have to do some work before we get there. So before we study these circular functions, we have to consider angles of rotation. And what we mean by this is we have this Cartesian plane, and we have 0, 0 here, and we have what we call this initial arm here, and we have what this is called over here a terminal arm. And if we open the initial arm up, imagine like it's sitting like this. If we begin to spin it in this counterclockwise manner, it starts here and it spins, and it could stop, and it could really stop anywhere. We have where it starts and where it terminates. This is sort of the structure, and the opening between the two arms, between this one and this one, this opening is theta. That's our angle. So what we see right off the bat, of course, is that theta can be much bigger than 90. So before we had triangles drawn, with 30 degrees or 40 or whatever, 60 and 80. But now we can, 90, and now we can actually get larger than 90, and we can keep going. Now, the three primary trig ratios have been defined for right triangles, which we know, and they've been built around this primary angle theta, which has been less than 90. But the thing is, if we allow theta to grow past 90, then we can actually extend our trig ratios to a whole number of other triangles or applications. Triangles that contain an angle greater than 90 are what we say are drawn in this standard position. So all we're saying is that we don't want to limit ourselves just to these triangles with these angles less than 90. We're going to actually begin to have different kinds of triangles. So to draw an angle in standard position, we have an object spinning around in a circle. So what we're trying to talk about now is the rules of trigonometry, which are triangles, and how we link them into things moving in circles. We're trying to essentially attach triangles and circles together. It's kind of like, square peg, round hole, but we make it work. You'll see, it works. If the dot, now imagine the dot was to stop in any position. So this thing is spinning around in a circle, and we were to freeze it, and this blue dot would stop here. And from that spot, we can actually draw a right triangle. We can have one corner down here on the origin, we have one corner up here on the edge of the circle, and we can drop a vertical line and a horizontal line to create a right triangle. So one vertex is on the origin and the other is on the dot's path, then a right angle would sit on the x-axis. Now once a triangle is drawn, as soon as we have a triangle, we can now get back into our world of the three primary trig ratios in terms of the position of P, of this point. Because once this triangle is drawn, we can throw a theta back in there, and we can say, okay, this is theta, I know SOHCAHTOA, I can now get some information and figure out that point, essentially the coordinate of that point. That's what we're aiming for. Now these definitions, once defined in terms of the position of the rotating point P, it's actually interesting. They're going to hold true for any position, including the angles greater than 90. So we're going to limit ourselves sort of this first quadrant, but the rules that we build for this first quadrant actually are true for everywhere around the circle, which is good. Good news for us. So you want to take the slide down here. An angle in standard position is defined like this. Okay. We have this initial arm, we have this terminal arm, and we have this point floating on the edge of the circle, xy. And between the two arms, we have our angle theta. Now we rotate the arm counterclockwise for positive angles. So for example, if I say draw the angle 120 degrees in standard position, we start here at the initial arm, we have the terminal arm, and we have to label that theta. So this is 120. You can label it in there, or you can label it out there, it depends. But this opening would be the 120 degrees. 260. Now we get into circles. That's 90 there, and then a little bit less down there to get my angle. And I actually have to draw. I got to draw an arrow and attach that label of 260. So I know that I'm talking about this part here. If I had a negative 200, it just means we go the other direction. So negative 90, negative 180, and then maybe hit negative 200 there. Now for these, we can redefine the three primary trig ratios. I'm going to call the opposite side as y and the adjacent side as x, so x and y. And I'm going to replace hypotenuse with r, with radius. So our SOHCAHTOA, SOHCAHTOA, opposite and adjacent and so on, they just essentially just get changed into the exact same structure, just different labels. So the opposite's now y, the adjacent, is now x, and the radius is now r. That's all. Now there's two interesting properties that arise from when you start spinning these terminal arms bigger than 90 degrees. So I'm going to draw an angle 50 degrees in standard position. That's easy enough. And then I have an x and a y and r. So there's 50 degrees, that's the opening, straightforward. Now consider the sine ratio, y over r. Where else in the circle could I have? I have a point here, I have y over r, but there's somewhere else all around the circle that I could use the same y and the same r, but have a different angle. And that point is over here, is a reflection along the x-axis, the y-axis. So this is my y, this is my y, there's my r, and there's my r. I have 50 degrees here. Now the question is, what angle is that? Well, if I know the whole thing is 180, and if I know that's 50 degrees in there, then that angle is 130. So there to there would be 130. And what we're seeing here is called the property of sines. So when sine theta is equal to a value, there are two values of theta that are going to satisfy the equation that are going to work. So for example, on your calculator, try the sine of 30 and try the sine of 150. And what you're going to get is the exact same value, the exact same ratio, because these two triangles exist. It looks like this. It's here and it's here. This one here. There's two triangles. There's the 50 degree one here, and there's the 130 one, the bigger one there, 130. Because sine uses y over r, right? Opposite over hypotenuse, y over r. So there's this y over r, or there's this y over r. There's actually two triangles. There's two of them. So the question is, of course, which one's right? Which triangle do I want? Do I want this one? Do I want this one? And the answer is, it depends. It depends on the situation you're looking at and so on. So that creates what's called the property of sines. Okay. Now by default, the calculator, fortunately, all the calculators agree, the calculators all go for the lower angle. Okay, so the calculators are all going to give you, assume you have this lower triangle. Okay, what about the cosine ratio? If I have this triangle, cosine is adjacent over hypotenuse, x over r. Is there somewhere else in the triangle that uses the same x and the same r? That would be down here at the bottom, right? I can have my positive x and my r to there, or my positive x and my r to there. So the question is, what angle is that? Well, if I'm 50 degrees up, I would be 50 degrees down. So if I know my whole circle is 360, obviously around the entire circle is 360, I've used up 50, I'm left with 310. So same thing, on your calculator, if you want, try cosine of 50 and try cosine of 310. You'll get the same ratio, the same value, because they're both using this value and this value. This is called the property of cosines. And you have, again, try cosine 50 and cosine 310 on your calculator. It'll give you the same ratio. A few last things here. We label the quadrants. This is quadrant 1, so Q1. We start in the upper right quadrant. Again, we continue going counterclockwise. So Q1, Q2, Q3, and Q4. And this is called the cast rule that we're looking at here. So imagine the word cast. And this just tells us where the trig ratios are positive. So they're all positive in this quadrant. Sine is positive in that one. Tan is positive in that one. And cosine is positive in that one. That's what the cast rule states. That pops up every now and again. And then the last idea here, angles that are said to be coterminal, co is share, coterminal, where the position of P is the same for each angle. So I could have 60 degrees, or I could add 360. Basically, I could spin it all the way around, and I could have 420 degrees. And those would be the same values. So again, on your calculator, again, you could type in sine 60, you could type in sine 420, and you'll get the same ratio. Now, of course, some angles are much more important to us than others. And the most important angles are going to be summarized in what we call the unit circle, which is the next lesson. So move on to the unit circle.